Let's understand ionic equilibrium in this video. Have you ever noticed how salt disappears in water? Or how adding salt can make soap form scum? These are examples of ions at work, and they come from a balance called ionic equilibrium. Ionic equilibrium happens when molecules and the ions they make exist together, and both keep forming and reforming at the same rate. In simple terms, some substances split into ions in a polar solvent like water, and the forward and reverse processes balance each other. There are two main kinds of ionizing reactions. One, where polar covalent molecules ionize, like acids and bases, and another where ionic solids dissociate into cations and anions. At equilibrium, reactants and products coexist, and the rates of the forward and reverse processes are equal. So nothing stops changing, but net concentrations stay steady. Substances that do not make ions when they dissolve are called non-electrolytes, for example, sugar, and they do not conduct electricity. Substances that do produce ions are called electrolytes, and they conduct electricity in solution or when molten. For example, sodium chloride, hydrochloric acid, and sodium hydroxide. Electrolytes are further split into strong electrolytes, which almost fully dissociate, and weak electrolytes, which only partially ionize and set up a true equilibrium. Let us look at a key idea for weak electrolytes, called Ostwald's dilution law. Consider a weak electrolyte with initial concentration C and let alpha represent the fraction that dissociates, called degree of dissociation. At equilibrium, the positive ion concentration equals C times alpha, and the negative ion concentration equals C times alpha, while undissociated molecules equal C times the quantity 1 minus alpha. The dissociation constant K equals the product of the ion concentrations divided by the undissociated concentration. So K equals C times alpha squared divided by the quantity 1 minus alpha. For very weak electrolytes, alpha is small, so 1 minus alpha is about 1, and then K approximately equals C times alpha squared, giving alpha approximately equal to the square root of the quantity K divided by C. This shows that as we dilute the solution, the concentration C falls and alpha increases, meaning dilution favors ionization for weak electrolytes. Now let us try a simple worked idea using the same steps. Imagine C equals 1 molar and K equals 1 times 10 to the minus 6. Then alpha is the square root of the quantity K divided by C, giving alpha equal to the square root of 1 times 10 to the minus 6 or 1 times 10 to the minus 3. So 1 out of 1,000 molecules ionizes. The degree of dissociation alpha is the fraction of original molecules that form ions at equilibrium, and we can express it as a fraction or a percent. Several factors affect ionization, including the nature of the electrolyte, the polarity or dielectric of the solvent, dilution, temperature, and the presence of a common ion. The common ion effect means adding a salt with an ion already present shifts the equilibrium back toward undissociated molecules, so ionization or solubility falls. For example, adding ammonium chloride increases ammonium ion concentration and reduces ionization of ammonium hydroxide, shifting the equilibrium to the left. Salting out of soap is another example, where added sodium chloride increases sodium ion concentration and reduces soap solubility, causing it to precipitate. The Solvay process uses related ideas, where reactions in ammoniacal brine and shifts in equilibrium lead to precipitation of sodium bicarbonate, which is then collected. Buffers resist pH change, and they usually contain a weak acid and its conjugate base. Adding the conjugate ion changes the equilibrium by the common ion effect and stabilizes pH. For an acetic acid acetate buffer, adding acetate ion shifts the equilibrium of acetic acid to the left, lowering hydrogen ion concentration and raising pH. The Henderson-Hasselbalch relation links pH to concentrations. pH equals pKa plus log of the quantity concentration of the conjugate base divided by concentration of the weak acid. And this helps design buffers. Solubility equilibria use the solubility product constant, KSP, which equals the product of the equilibrium concentrations of the ions for a sparingly soluble salt at a given temperature. For example, for barium sulfate, KSP equals the concentration of barium 2 plus times the concentration of sulfate 2 minus. Factors that affect measured KSP include the common ion effect, the diverse ion effect, and formation of ion pairs or changes in activity coefficients, while true thermodynamic KSP depends on temperature. So what do we learn from this? We learn that ionic equilibrium links ion formation, dilution, common ions, solvent effects, and solubility to explain acids, bases, buffers, and precipitation. Let us quickly remember. Electrolytes may be strong or weak. Ostwald's law shows alpha increases on dilution. Common ions suppress ionization. Buffers resist pH change, and KSP controls solubility. Thank you for listening. Keep exploring these ideas with practice, and remember, small steps help build big understanding. For more clear examples and guided practice, do take a look at the related lessons on EduRev. And keep asking questions gently as you study.